Hello everyone, welcome again to my channel Learning from Data. Today I am going to talk about simple linear regression in R. I will explain what are the output of a simple linear regression in R, and those parameters will be explained in details. Let's first talk about what do we mean by simple linear regression. Simple linear regression is a special type of linear regression where we have only one independent variable and only one dependent variable. That means we plot the independent variable along x-axis and we plot the dependent variable along y-axis, and we try to fit the data with a line. That is the simplest form of linear regression. One example is shown here in this picture, where we have some data points and we try to fit the data points with a line. A line has a slope and also has an intercept value. So in linear regression, we try to determine these two values, the value of the slope and the value of the intercept. And how this is done? This is done by trying to minimize the error. What do you mean by that? Let's say we have these data points over here and we try to fit these data points with a line, and some of those data points are above that line and some of those data points are below that line. For the data points which are below the estimated line, for example, for this data point we have actually overestimated this data point. That means the actual value is here, but we have predicted the value to be here along this line. Therefore, the error for this data point is negative. On the other hand, for this data point, we have underestimated this value. Therefore, the error for this data point is positive. And we can have both positive and negative error for all the data points, and we try to get the square of those errors. We calculate the squares of all the errors for all the data points along the line, and we square those errors, and since we are squaring those errors, all the values become positive, and we try to minimize that sum of squared error, and only one line that satisfies the condition is our target line. In this example, we have this line with slope of 2 and intercept of 4. For the purpose of demonstration in R, I will take a very simple dataset. This dataset is downloaded from Kaggle, which has 2 columns only. In column A we have years of experience, and in column B we have salary. We'll try to fit this data in R and see how the linear regression output works there, and we'll try to explain all those parameters one by one in details. Alright, here we have our studio open. I have first imported the ggplot2 library to plot the data. Then I have the read.csv command to read the salary.csv data. Let's look at the first few rows of the data. Okay, we have years of experience and salary column, both look good. Next, I'm going to plot the salary against years of experience. On the right side, you can see that the salary and the years of experience plotted. The salary is quite linear when plotted against years of experience, so the linearity is there. Therefore, we can say that the salary increases or decreases linearly with years of experience, and this is very rational, because the more the years of experience, the higher the salary should be. Okay, then we can implement this linear model function. Let's run this one. So all it says is we have the salary, that is the dependent variable, and the years of experience, which is the independent variable, and we have the data set here. So let's run this one and get the summary from here. Now I'm going to explain all the parameters that the summary has given us as an output. So let's make it a little bigger. Okay, so in the first column we have the call, that is the linear model call. The formula is written here. Next we have the residuals. So I have first shown you that in a linear regression all we want is a linear fit of the data, and there are some positive and negative error as well along the data points. So these residuals value shows us the statistics of those errors. So minimum value is this value, that means we have minimum error which is negative, and we have also the maximum error which is this one, which is on the positive side, and we have also Q1, the Q2, that is median, and Q3 also here. So those are written as 1Q, basically those are first quartile, and median, which is the second quartile, and 3Q, which is basically the third quartile. So the residuals statistics are given here. Next we have the coefficients data. We have the estimate column, and in the rows we have the intercept and the years of experience. Since we have only one independent variable and we're talking about simple linear regression, we only have intercept here and only one variable here, and the estimates are given here. The intercept estimate is this value, and the slope or the coefficient of years of experience is given here. We are also given the standard error, which are the error for each of the independent variable as well as the intercept. So what does it mean? The standard error is the measure of variability of these independent variables and the intercept. In other words, we can say that the standard error is the value that determines how precisely the estimates are measured. Therefore, this is the precision of this estimate. So these are the precision of these coefficients. If we have multiple linear regression, we will have multiple standard errors as well. Next we have the t-value column, that is the t statistics, which is this estimate divided by the standard error. And next we have the p-value column, and this is calculated depending on the t-value and the degrees of freedom. We are shown here that we have 28 degrees of freedom, and depending on that value and considering this t-value, we can go to the t-distribution table and find out the p-value. Here the significance codes are given here, that is 3 star, 2 star, 1 star. So 3 star means very, very significant, and the significance reduces as the number of stars reduces. And in our case we have 3 star both in both cases, both in intercept as well as in our years of experience estimate. Therefore both are very, very significant in our data. Next, we have the residual standard error. So this is the standard error, or we can say the standard deviation of all the residuals. The residuals statistics are shown here. So we have the residuals here, and this number shows the standard error or the standard deviation of these residuals. And we have degrees of freedom here given as well. Next, we have multiple r squared value and also adjusted r squared value. So the multiple r squared value is a measure of how the data is fit, or we can say that it is a measure of goodness of fit. In other words, this is also called coefficient of determination. That means how much variability is being explained by the independent variable. In this case, we have only one. So 0.957 means 95.7% variability are being explained by this only one variable, that is years of experience in our case. Adjusted r square is pretty much same in our case because we only have one independent variable. But if we have multiple variables, some of those independent variables may not be as significant as years of experience. In those cases, what adjusted r squared do, this procedure actually penalizes the addition of more variables in our dataset, which are actually not contributing enough towards explaining the variability. So adjusted r square will be less if we have multiple linear regression, and that means if we have more and more variables added up here. Of course, if we had more and more variables, the multiple r squared will increase, but adjusted r square will penalize those addition, and it will adjust this r square and give us the corrected value. Finally, we have the f statistic value here, and the p-value of that test is given here. F statistic tests whether the overall model with one predictor, in this case, can significantly predict the dependent variable. So there are some hypotheses here, and we calculate the p-value for that hypothesis test. Let me explain a bit more for the previous hypothesis test over here, since we also have a p-value calculated here. In this case, the null hypothesis for the coefficient estimate is the null hypothesis states that the coefficient estimate is 0. That means it doesn't have any impact on the dependent variable. And the alternate hypothesis says that these estimates have significant impact on the dependent variable. And since we have p-value a lot less, that means which is indicating that these independent variables are very much significant, and we can reject the null hypothesis. In this case of f statistic, the null hypothesis says that the overall model can significantly predict the overall model cannot significantly predict the dependent variable. That means the contribution from the overall model is not significant at all. But the alternate hypothesis says that the contribution from this overall model can be significant to predict the dependent variable. In our case, that is salary. So we have this test done here, and we calculated the p-value, which is also lot less than 0.05. So in this case we can reject the null hypothesis as well, and we can say that this overall model with only one independent variable, which is years of experience in our case, can significantly predict the dependent variable, which is salary in this example. All right, we have explained all the output variables from this linear model command in R, and I have also another video for Python's stats model output. You can also check that one to get the explanation on the parameters that were given output from Python's stats model library, and you can compare these two as well. Thanks for watching this. Hope to see you in the next video.